This is the first in our series of videos on what are called confidence intervals. And before introducing the confidence intervals, we need to talk about what we mean by an estimator. So this whole idea of inference that we've been talking about recently is about drawing conclusions from a sample about an entire population. So if I take a random sample with replacement, I can calculate some sample statistic. So let's say I want to calculate sample mean. That is an estimate of the actual population mean. So typically, I don't usually know the population parameter because it would require getting a census of everyone in the population. If I knew the population parameter, there's no need for inference. So this whole process that we're describing is because we only have a simple sample and we're trying to use the information from the sample to make some type of conclusion about the unknown population. Notice that I could have gotten a different sample mean because I took a random sample. And so this statistic, the sample mean, is actually its own random variable. So one way we've been thinking about this so far is you're randomly drawing a sample, computing the statistic for that sample, and using that to get a mean. So that's what's happening here. But another way that I could picture this is I have an entire distribution of sample means. So this is the sampling distribution of my sample mean right here. And when I take a sample and calculate the sample mean, I'm really just drawing from the distribution of the statistic. So this 5.82 is just one of the possible values I could get for sample mean, and it comes from this distribution. Which means if I had gotten a different, let me back up. So we often use the second view instead of the first because we're trying to interpret this estimator directly. Now I could have gotten a different number than the 5.82. If I do this again, let's say I get 5.74. This, as an example, is my sample distribution, right? And then from the sample distribution, I'm getting a sample mean. Again, but I can think of that sample mean as just one draw from the sampling distribution of the sample mean. Now I have some interesting questions I want to ask about this sample mean. If I use the sample mean to estimate my population mean, how good of an estimator is it? And mathematically, we have two ways that we measure how good an estimator is. Okay, so in general, let's suppose I'm trying to estimate some population parameter theta, and I'm using the estimator theta hat. You'll see this notation quite frequently when we're talking about an estimator. A lot of times we'll put hats on them. So two of the questions I could ask are, do we get the right answer on average? So is this estimator what we call unbiased? And how variable is the answer? So let's look at the visual first, and then we'll go to the mathematical definitions. Imagine the actual parameter here as being the center of the bullseye, right? And that's what I'm trying to hit. That's the target I want. My estimates, can you imagine them as the darts that I'm throwing, that I'm getting from taking samples and calculating some statistic? That's represented here by the little X's. If my estimator has low bias and low variance, which is kind of the ideal world, I likely are going to have a lot of my darts centered right around the bullseye and close to it. I could still have low bias and high variance though if I'm still centered around the bullseye, but I'm not as close anymore. So my spread is a little further. High bias and low variance, the bias means I have all of my targets or all my darts here definitely clustered together, so they have low variance, but they're not centered on the actual bullseye. That's high bias. And then high bias, high variance, well, I'm not centered at the bullseye, and I have a lot of variation in where my darts are. So this is the ideal situation. We're trying to go for low bias and low variance. And in particular, we define the bias as the average of the sampling distribution for the statistic minus the actual parameter. So An estimator is called unbiased if the bias is 0, which would mean that the average of your sampling distribution, or your expected value of your estimator, exactly equals your parameter. So that's an ideal situation. But again, we can still have low or 0 bias and have a lot of variance. So the other thing I need to measure is how variable is the answer. So suppose we're trying to estimate the population mean. So for example, I could try to estimate the average height of undergraduates. I can collect a simple sample, but it just has one average. And since that sample was random, it could have come out differently. Here is an example of the sampling distribution of the sample means for two different sample sizes, sample size of 200 versus 800. And we saw this phenomenon when we introduced the central limit theorem. So one thing I want to point out is I'm interested in not only the sample mean itself, but what is its average and what is its spread. Let's look first at the average of the sample mean. We showed, when introducing the central limit theorem, that mathematically this is equal to, okay, I can bring the 1 over n out front, and then I have the sum of the expected values, but each of those random variables have the same expected value from some population. We're going to call it mu. And so this ends up being n times mu, and from that sum divided by n. At the end of the day, I get mu as my expected value for this sample mean, which you can see in the picture, right? It's centered at the same center as the population. So that means that the sample mean is an unbiased estimator of the population mean. Let's look at this in the context of some of the demos that we did with the central limit theorem. Okay, so if you recall, we could make any starting distribution for our population. So I have just two random distributions here. And when I go and take the sampling distribution of the sample means, here I'm doing sample sizes of 5. Here I'm doing sample sizes of 25. And we can see two things that happen. Number one, by the central limit theorem, the shape of these sampling distributions are normal. And when n is 5, it's not necessarily guaranteed that the central limit theorem is going to pop in or apply, because this really works as n gets larger. But even in this simple case, they look roughly bell-shaped. But we also notice that the center of these distributions align. So here's the mean, there's the mean. It directly aligns with the mean of my original distribution. Same thing here. The mean of, the mean was in blue. So let's fix that. Right, there's the mean. All right, so here's my mean in blue for this one. And you notice that it lines up with the means roughly, right? I have 13.99, 13.98. They're very close. But that's what we saw analytically on the previous page, and that is a way to visualize this idea of unbiased estimator. If I repeat the sampling process many times, the expected value of our estimates should be equal to the true values we're trying to estimate. All right, so that's a nice property. That's not true for all estimators, but it is true for the sample mean. Now let's talk about the spread of the sample mean distributions. So what do we notice going from, say, n equals 5 to n equals 25? And we talked about this again when we did central limit theorem, that the spread is going to decrease as you increase your number of samples. But let's remind ourselves why from the theory. So I'm taking the variance of my sample mean, that's a sum of these random variables divided by n. When you take the variance of a constant, so I'll remind yourself here, if you have the variance of a constant times a random variable, this ends up being a squared times the variance of x. And you can rederive that just using the definition of variance. But the intuition is, remember, variance involves a squaring of the difference between a random variable and its expected value. So that's where that's coming from here. And then a sum, I want the variance of sums, it will equal the sum of variances as long as my covariances are 0. And because these are independent, identically distributed, our sample, we're assuming we're doing a random sample, then our covariance are 0. And so then this is going to be the variance of the original population, which is n times the variance there. And so at the end of the day, the variance of the sample mean ends up being the variance of my original population divided by n, which means my standard error, which is standard error, again, is the name we give for a statistic. When we're talking about the distribution of a statistic, it's the standard deviation of that statistic. Standard error is equal to the standard deviation of the population divided by square root of n. And that's why we see less spread here as I increase n. Okay, so nice characteristics here of the sample mean as an estimator for our population mean. Number 1, it's unbiased. And number 2, we can decrease the standard error by increasing the sample size. So both of those characteristics, the bias and the spread, are going to be something that we can take into account when we're deciding what type of estimator to use. And then to really incorporate the spread information, we're going to give our answer, instead of just as an estimator, we're going to give it as an interval around the estimator that incorporates the standard error. And that's what's happening with confidence intervals. So this leads us to define what is a confidence interval, and that'll be in our next video.